Okay, so we're gonna have this exercise now, which works with independence, right? They're telling us that we have x1 and x2, which are independent and uniformly distributed from 0 to k, with k equal to a natural number. And we define a random variable, which is a piecewise function, which states that this is going to be equal to x, well, x3 is going to be equal to x plus 1, x1, sorry, plus x2, if, right, the sum is between a range from 0 to k. That's it. And well, this is going to be the other case where we say it's going to be equal to this otherwise, if we are not in this range. So the first exercise is quite challenging, I have to admit. Says, show that x1, x2, and x3 are pairwise independent. So the first thing we're going to note is what independency means. Independence means that if we have, for example, right here, it states that x1 and x2 are independent. So this means that the probability of x1 and x2 happening, which is the same as saying the intersection, right? This is the same thing, is going to be equal to x1 times x2. That's it. That's simply put in simple words what it means to be independent. So this is independence. Right? That's pretty much it. Now, we want to show in number 1 that x1, x2, and x3 are pairwise independent, but we want to show this by first understanding what the distribution of x3 is. That is the most challenging part, surprisingly, but we'll go step by step. So let's go ahead and first find simply put the how you call this distribution of x3. So let's start with x1. We know, let's find out that the distribution of x1 and x2. It says here that they're gleich verteilt, meaning they're uniformly distributed, like they have the same, from 0 to k. Meaning it's like a dice, right? If we have a dice and we have 6 faces in the dice, a dice are not dice, it's a plural form. If we have a die and we have 6 faces, what's the probability of us getting the number 1? Well, it's 1 over 6, right? So it's basically the number of valid cases that we want over the number of possible cases, right? So in this case, we're simply going to do, they're telling us that both x1 and x2 are from the range of 0 to k. So let's look at that. It says here that it's from 0 to k. So let's look at 0 to k. What does 0 to k mean in this case? Let's just copy this. Oops. I'll just copy this little guy so we can paste it over here. So have it nicely with a nice little image. So what do we have here? What's the size of this? Size. So imagine we have, I don't know, from 0 to 3, where k equals to 3. 1, 2, 3, 4. Oh, sorry, 3. So how many elements do we have? We have 1, 2, 3, 4. Meaning we have one more than what k has. So we can simply say that the size of this is going to be basically k plus 1, right? And that's pretty much what we're saying. So we know it's uniformly distributed, so it's going to be 1 over k plus 1. That's going to be simply put our distribution for both px1 equals to x and px2 equal to y for simplification purposes. And that's pretty much it, right? It's really not that difficult to understand how we find this, right? If you want to find the actual formula for this, this would be 1 b minus a plus 1. In this case, it's from 0 to k. So this is going to be b, this is going to be a. So it's equal to 1k minus 0 plus 1, which is just k plus 1, right? That's simply what we want. So that's it. That's the first part that we needed in order to start finding our probability. Now, what is x3 defined as? Let's take a little guy here. We copy it, we paste it. What is this defined as? Well, simply put, we have two cases, right? We have one case, we're going to mark it as orange, where it's like this. And then we have another case, we're going to mark it as blue. So the orange case, right? So px x3 equals to whatever value, let's call it I, right? Whenever px, right, ex1 is going to be equal to I plus px, yes, x1 plus x2 minus k plus 1 is equal to I. So whenever we have a piecewise function, we have to understand that these are like an OR cases. So it could be if we have this case or this case. And when we have an OR situation, we use a plus. So that's simply put what we did, right? Now we want to clear for x1 and x2. So we want to move this guy over to the other side. So let's do that. Let's duplicate this. So we will have, simply put, if we erase this, erase that, plus, right, plus this. So we have two different cases, right? That's what we want to do. So now that we have done this, we want to first focus on the orange case. So this guy over here. And this is going to be the blue case. So let's just mark it as that. So let's start with the orange case. What does this mean? Oops. We can equalize it. And we know for a fact that we can have two cases in this case. What we're asking is how many pairs x1, x2 exist such that x1 plus x2 is equal to I? That is the question. So let's do first the base case, right? Let's use the base case. So we know for a fact that this guy, all of this guy, is going to be equal to I, as we have denoted here. This one is equal to I, so we can write I here. So I. And we take the base case where I is lower or equal to k. So the base case is when I lower or equal to k, right? And that's it. So let's denote the following things. So x1 is going to be equal to x, x2 is going to be equal to y. And what we do is simply put, okay, let's take x plus y is equal to I, right? Now clear for y. Okay, this means we have minus x, right? And now this, we know for a fact that y is between 0 and k, meaning that we have 0, y, and k, meaning that we can put this definition into here, right? Like so. Not too shabby, not that difficult. Now, let's clear for x in each case. So the first case is going to be the left side. So this left side. This is going to be equal to, well, we're going to solve inequality, so to speak. So what we do is we put the x on the other side. So we're going to have y, I think it's like this. Let me, base case, let me think of this. Yeah, simply put, we can move it. Let me think. No, actually, we can just put the x's. Well, yeah. Simply put, yeah, that works. And now we take the right side. And this means that x, we're going to change the sign of this. So it's going to be greater than. And this is going to be I minus k, right? Now, we want to focus that x also has to be from 0 to k. As we have stated from the exercise, it says here that both x and x2, x1 and x2, which in this case, if you remember that we denoted, this is going to be x, this is going to be y. They're obviously distributed in the same way, so from 0 and k, right? We continue on. So I just wanted to like remember where this comes from. And given this means that, well, this little guy, we're going to translate it into the n type of like format. And this means that x has to be lower or equal to I, right? And then x has to be greater, so meaning it starts from I or equal to this. So this goes to infinity, right? So what do we do here? We're going to search now the bounds, right? We know for a fact that we started at the base case where I is lower or equal to k, meaning that what is the smallest thing that we have? So what is the one that like, what is the intersection of all of these guys, right? So in this case, if we do the intersection of all of these groups, so to speak, from this one and this one and this one, we'll see that x is going to be from I minus k, right? And then it stops at k, because, yeah. So we can finish that as such, if I remember well, yeah? However, one thing that's really important is that in this case, actually I should have done this earlier. Let me just erase all of this actually. I did a big mistake. I'm looking at my notes right here. Let's erase this little guy and see this. I minus x, right, should cancel out. Why? Because x1 plus x2, meaning x plus y, has to be equal to I that's lower than k, right? So if I is lower than k, then it means, right, that I minus k, oh crap, I bet it made a big mistake. Holy smokes. Oh man. Okay, let's just redo this from the start. So sorry, you guys. I did a simple mistake. So we start from the left side. Left side like that. Left side, what does it tell us? It tells us basically that x is going to be lower or equal to I. Right? That's a simple, the solution. And this guy is going to tell us that, first of all, x is lower, well, minus x is lower, and then minus I, and then we change the sign, so I minus k, right? Meaning that we have, so to speak, x is going to be greater minus k. So now we apply, again, the thing that we said, So has to be like this, and x is going to be greater than I minus k to infinity. And then we have x from 0 to k. We find the intersection, so to speak. So we start from x, I minus k, yeah. And in this case, we know that I is lower than k. So I minus k will be a negative number, right? If we know that I is lower than k, meaning any I, right? Imagine we have, it can be 0, it could be like, I don't know, 3 is lower than 8. So 8 minus 3 is going to be, oops. No, 3 minus 8 is going to be minus 5. So in this case, this will be minus 5, right? And we don't want that. So simply put, we can ignore this case because it will not be within the probability case because it's in a negative number. So this one we can cancel out. We can just ignore, right? Now let's check only these two, right? Let me check these two. It says that we start from 0 to k, x starts from 0 to I. We know for a fact that I is more than k, so this is the intersection, so x has to be between 0 and I, right? And now we want to find the distance between 0 and I. And to find the distance, we just do basically b minus a. So in this case, if you remember, this is going to be a, this is going to be b. So it's going to be I minus 0, right? And that's it. That's going to be the distance. But if we want to check out how many values we have between 0 to I, we have to include 1, right? So at the end, we will have I plus 1. So that's pretty much what we wanted. And we can follow up to the next case. Now, the next case is going to be whenever we have I greater than k. So other case, I greater than k. And we do the same logic. So we can actually copy this. Let me just erase all of this because it's going to confuse us. Let's just take all of this. We paste it here. We do the same logic, right? And yeah, we do the same logic. Same logic actually over here. We just move it like so. And that's pretty much about it. Now, what we want to do is simply put, okay, we have this. Now what, right? So what we want to do is, how do you call this? Yeah, just solve for x, right? The other case is going to be solving for x as well. Simple. So it's going to be, again, x is going to be greater or equal to I, not lower or equal to I, and x is going to be greater or equal to I minus k. So in this case, what defines the difference is the fact that we have I, k, and x has to be between 0 and k. So it's no longer that our subtraction here, our subtraction will be like a minus number. Therefore, we can say that x can be from 0 to I, and x can be from I minus k to infinity. So if we put all of these together, and we find the intersection between all of these domains, we can see that x is going to be an I minus k, right, to k. Oops. Till k. Again, we find the distance, and not only the distance, but how many values we have in this little range. So this is easily k minus I minus k plus 1, which would equal to k minus, plus k minus I plus 1, 2k minus I plus 1, right? That's pretty much it. Now, we know for a fact that we want to find the probability of x1 on x2. So it says how many pairs do we have, right? And what is the probability of this? So the valid pairs that we have are I plus 1 in this case, and 2k minus I plus 1. That's the other valid case. But we want to divide this number amongst all the possible cases. And because we have a pair of numbers, and because they're, a pair of numbers and they're independent variables, we can divide each of these, right, over k plus 1 squared. Why k plus 1 squared? Because remember that the probability of x1 times the probability of x2 is equal to 1k plus 1 plus 1 k plus 1 squared. So that's what we're placing there to just, that's a possible case, so to speak. So we have found this. All good. We have found this little bad boy. And this is also gonna be over 2, k plus 1 squared. That's pretty much it. So we are done with the orange case. With the orange case, we are done. So we have to repeat the same thing, but with the blue case, right? So the blue case, we can do base case. Okay, let's just copy the blue case. So let's just get this guy. So again, let's just rewrite before we go with the blue case. Let's write what the orange case is, right? So the orange case, copy. The orange case is going to be this one. And it's a pairwise function that states, okay, we're going to take this one, copy. We're going to take this little bad boy. Whenever k I is equal to k, and I is greater than k. So these ones are piecewise functions. Now we're going to do the same thing for the blue case. So the blue case is going to be quite interesting. So we do the same thing, right? So base case, where I, in this case, I plus k plus 1 is lower equal to k, right? And if you notice, this is like quite weird because we're saying, yeah, how this is a case where we take this number that is, say, imagine this is 4, right? Imagine this number, this value is 4, and we're taking the same number 4. What's the probability of finding like some pairs that when you add, you get a smaller number than 4? It makes no sense because we're not working with negative numbers in this case. So it's not possible. Therefore, this is equal to 0, the base case. So this is equal to 0. Pretty simple. Now let's do the next case, which says other case. A plus k plus 1. And then we can actually work with this now. This one we can actually work with. So let's do that. So the other case is the same situation. So where's this thing? Give me this. Actually, let's just start from the beginning. So let's say x1 is equal to x, or x2 is equal to y. And then we're going to do x plus 1, x2, well, we can just do x plus y is equal to I plus k plus 1, right? We solve for y, so y is going to be equal to the same thing, minus x. We know that y is between 0 to k, meaning we do the following. we take 0, and then we take this little guy, copy it, duplicate it, put it there, call it a day, and K, right? Then we do the left side first. We focus on that. And oops, I forgot to add the X here. Quite important. And then the right case. So what does the left case say? Well, it's simply saying that we have to move the X to the other side. So something like that, right? And then in this case, we have to check the other one, which is going to be, we pass this over here, which is going to be X. Then K goes over there in a negative way. So X is greater than I plus 1, I reckon. Let me check. Other case. Let me just check this so I know I am correct. Hold on. Yeah, it's yeah, I plus 1. So like that. We know for a fact that we have that X has to be from 0 to K, right? And yeah, so we're gonna compare it with all the other guys. So let's put it over here, erase this. X starts from 0, so 0 up till I plus K plus 1. Then X has to be greater than this, so I plus 1 to infinity. We take the intersection of these three little guys, which means that X has to be between, we start from I plus 1, surely, and in this case we take I plus K plus 1, I reckon. No, hold on. Oh no, we take K. We want to take the intersection, so K. So the smallest one. And simply put, we can find the distance, well, the elements of the range. Remember, it's going to be B minus A plus 1. So in this case, we're going to get, right, K minus I minus 1 plus 1. This translates to K minus I. So at the end, we can simply state that the blue guy here is not a piecewise function. Whenever, right, whenever we have X plus 1, okay, let me see. Yeah, so it's going to be 0 for I plus K plus 1 lower or equal to K. And the other case is going to be this amazing new function that we found, well, divided by obviously the amount of numbers that we have, so K plus 1 squared. So copy, paste, and this is going to be the opposite case, so like so. And we're done. We're done with finding the actual distribution. So whenever they ask us, okay, we have now the probability of x3 equaling K, where do we go? Okay, let's check it out. So this means x1 plus x2. Why? Because we know for a fact that if it falls between the range of 0 and K, which in this case we do, because K is equal to K, we take this function, right? So we take that, it's equal to K. And what do we do now? Well, in this case, we want to see whenever we have this scenario. So we gotta check the orange scenario. Why? Because we say x1 plus x2 is this. And when do we choose each function is whenever I is lower or equal to K. In this case, the I we chose is K, so K equals to K, meaning we take this little function here. So let's equalize it. paste it. And look at that. That's our function thing. In this case, it's not I, rather k, because we're inputting a variable. So as you can see, this and this are pretty much the same. So we can do 1 k plus 1. So at the end, we have finally found that x3 equals k is equal to 1 plus k. So that's the most important part of the exercise, actually. The actual proof is not that difficult. So then now we want to prove the pairwise independence, right? The pairwise independence, if you remember how I explained it earlier, it states that, this, right? With any random variable. So in this case, x3, whatever. Oh. So let's do that, right? Let's take the case where x1 is going to be equal to I and x3 is going to be equal to L. So let's see what happens whenever x3 is greater than x1, meaning L is greater than I. Then it means that if we subtract these two numbers, right, this is going to be in the range of 0 to k, because a bigger number subtracted by a lesser number will always be positive. Then we have the other case, right, which states, hold on, let me just see, yeah. So we know for a fact that x1 and x2 equals to x3. So we know that x2 for a fact is x3 minus x2. So that's what we wanted to do, actually, right? Let me just move this a bit so you can understand it better. So this is the first step. I didn't do it because I was stupid, but that's basically what we want to do. First, get the original definition of x3, and then x3 is equal to this. So if we clear for x2, we'll get that. So now that we have x2, we check, okay, what happens whenever the x3 number is bigger than x2, the x1 number? This is x1. What happens when the x3 number is bigger than the x1 number? Well, the subtraction will be positive, right? What happens if the x3 number is lower than the x1 number? Then it means that L is lower than this, meaning that L minus I is going to be non-negative, like it's going to be negative. So is negative. So is, we can just write it is in, then, oh gosh, like that, something like that. I think we can write it like that. It's an integer that's negative. So what can we do? Well, simply put, we can wrap it around with k plus 1. K plus 1 will make a wrap around, right? And wrapping around means we make it positive again. So we can do Li plus k plus 1, and that's it. So we can denote this, we can actually say this, that this is equal to x2, right? And x1 is equal to, x2 is equal to L minus I. And we can do actually a little indicator function saying that L is greater than I. In this case, L is lower than I. Oops. So that's pretty much what we did right there. And now we want to see what the probability of x1 with I and x3 L is. So we can actually take, basically what we're saying is we know that x3 depends on x1 and x2. So in order for that to be, like x3 to be equal to L, then we need these XL2s, right? We need these two. Meaning that if we multiply them, we have this guy, x1 equal to I, and x2 is equal to this bad boy, right? Then we multiply it also by the indicator function. And we can also have the case, it's an OR case, because we can have either the case where x3 is greater than x1 or x3 is lower than x1. So to put another plus for the OR case is going to be the same thing, x1 equal I, x2, in this case I'm going to do L minus I plus K plus 1. In this case, we're going to do L I. Yeah. So we know that as these are independent, as these two guys are independent, x1 and x2 are independent as per the exercise. It states over here, x1 and x2 are independent. We know for a fact that this holds, right? That this holds. Thus, we can write, oh gosh, my finger, probability of x1, and then times probability of x2 plus probability of x1 equals I times probability of x2 equaling all of this crap. And then we can factorize x1, the probability of x1 is going to be factorized in this case, so we multiply this up. There we go. We're almost done, you guys. Really long exercise, really tedious, but quite interesting, I would say. Now that you have this, right? That's pretty simple, right? You can say, Hale, I know for a fact that, let me just think. Oh no, I don't factorize it. Well, yeah, actually I do factorize it. Let me just check the last step because I'm not sure what I did here. Let me just see. Well, simply put, you know, as they're independent, you basically are doing px1 equal I, right, times p times 1 over k plus 1. That's for x2, right? And this would be equal at the end to be 1 k plus 1 squared, right? And this would be the same as saying that x1 I times probability of x3 equaling I. It will be the same thing. Well, L, sorry. It will be the same thing. And that is about it. We only showed one case, right, with x1 and x2, x1 and x3, so we have to also check x1 and x2. Well, x1 and x3, no, x2 and x3, sorry. x2 and x3, and maybe, I don't know, and x1, right? We have to check all these other cases, which I'm not going to do here because, you know, but they're done with this analogously, so analog. Oops. To this. So that's basically how you do it for all the other two. We have to check it for all the other ones. And pairwise means that we can pair up each of the random variables and they're going to be independent, right? Now, let's go ahead and finish this exercise in a nice way. Where we show that x1, oops, there's going to be 2. Number 2 asks us, show that x1, x2, x3 are not independent. So all of them are not independent. So it's pretty easy, actually. So we do, imagine we have x1. We can do this by counterexample. Let's say this is this, x2 is 0, and x3 is 1. So in this case, what do we do, right? What's the probability in this case? Well, simply put, it's quite easy. This is not possible. Why? Because we know for a fact that x1 plus x2 is equal to some number, right? It's equal to x3, right? In this case, we're saying that x3 is 1 and x1 plus x2, right, are 0 and 0. And 0 and 0 are not the same. Therefore, we get an error. We're like, no, this doesn't add up. This doesn't add up. The probability of this happening can never happen. So we can just simply say that this is the probability of the empty set happening, which is equal to 0. And if we do probability of x1 0 times x2 0 times x3 0, right? This is going to be just all of them, right? Just multiplying them, and that is not equal to heckin' 0 at all. So we can simply say, hell, by counterexample, this doesn't add up. Now, one thing that I was just thinking, gosh, my back is killing me, mate. Yeah, is this part over here. Why are we not adding them together? I was just thinking about this one right now. And I was thinking, why are we not adding these together? Is because they're singular cases. They're mutually exclusive. You cannot have them both happening, so then you can get one of them cases. But whichever case you get, you're going to get the same PDF, or PMF in this case, and you're going to multiply them, so you get the same answer. So that's it. So yeah, that's pretty much about this video. It was god-awful to make it because it's really long, but yeah, that's pretty much it.